So our next paper, which there's an interesting story, because when I was reading the paper on the proceedings, like, oh, I've seen this research before, and it was, Eva actually told me that it was because 2 years ago she was presenting this in the doctoral symposium as some research she would be doing in the future, and now we have her here with a paper accepted, and actually it's nominated to the Best Paper Award, so actually that's a very good story for the conference. And the paper is about local item-to-item models for top-end recommendations and how to sort of expand on some of the work that has been done on SLIM. So Eva Christakopoulou from the University of Minnesota. Thank you.
Thank you. Hello, everyone. Thank you for coming. My name is Evangelia, and I'm going to present to you my work on local item-item models for top-end recommendation. This work was done in collaboration with my advisor, George Karypis, at the University of Minnesota Twin Cities. So first, a general overview of the talk. I'm going to motivate what I'm going to talk about, present the method, and then show the experimental evaluation, the results, and final conclusion. So motivation. All of you here, I'm sure, know of neighborhood methods. The neighborhood methods identify similar items or users. Between them, among them, the item-based methods are very well suited for the top-end recommendation task. And there different examples of item-based methods are KNN, so nearest neighbors, and then a more modern approach called SLIM. However, the existing item-based approaches share a common limitation, which is that they have the drawback of estimating only a single model for all of the users. However, there could be differences in users' behaviors, meaning that we could have diverse user preferences or even opposing user preferences that cannot really be captured by just a single model. So it would be better to actually have multiple item-item local models, so a different item-item model for a different user subset. So here in this example, we can just see the whole data set. It has on the top, it has like an item-item matrix, and then we separate the users into two different subsets, and we learn a different item-item model for each user subset. And now I'm going to give an example of when these multiple item-item models are beneficial. I'm going to use the word local to refer to them from now on. So here we can see two data sets, data set A and data set B. They both have two user subsets. Now, in the data set A, there is a set of items that has been rated by users of both subsets. However, in the data set B, we can see we have two disjoint user subsets that the items that every user subset has rated, they do not overlap with the items that the other user subset has rated. And so here, since we're talking about item-based methods, this means that we need to find the similarities between one item and another item. So let's suppose now, for the sake of this example, that the target item is the item I. So here, let's go and compute the similarities between item C and item I. If we do this locally for the users of subset A, we will see that this similarity has a value. Let's suppose now, without loss of generality, that this value is a high value. And let's go now and compute the similarity between items C and I for the users of subset B. This will have a 0 value. And now if we do it globally, we will see that the similarity of C and I will tend to be towards some average value. However, this will not be very good for the users of subset A, because when we go to compute the recommendations for these users, we will have lost the very useful information that item C and I are actually very similar. And so by just doing it globally, we'll lose this. However, if we do it locally for the users of subset A, we'll be able to use this kind of information. And this is an example of when the multiple item-item models is beneficial. Now let's take the similarities between items I and J. It's going to be the same both in dataset A and B. We will see that we'll have the same similarity value either computed locally for subset A or computed globally. So in this example, either we do it globally or we do it locally, we do not have difference in results. So this was the motivation. I don't know, sorry. We're supposed now to move on. Okay. Sneak preview. So our method now is an item-item method that computes top-end recommendations by learning a global item-item model and multiple item-item models, each item-item model for a specific user subset, and it also automatically identifies these user subsets. So now we're going to start talking about the method. Our method is called GLSLIM, which stands for Global and Local Sparse Linear Methods. And this is an item-based method that while we could start from any possible building block, we did not use an old-fashioned approach like item KNN. We use a more modern method, SLIM. But it could be any other item-based approach that we could use as the building block. So now, a few words on SLIM. SLIM stands for Sparse LInear Method, and it computes the item-item relations by estimating an items-by-items sparse aggregation coefficient matrix S. And the recommendation score of an unrated item I for a user U is computed as a sparse aggregation of the items that the user has rated in the past. And here we see in this example an example of an item-item matrix, and SI stands for the ith column of this matrix. And the optimization problem is that we minimize the error, and we also have L2 and L1 regularization to prevent overfitting and to enforce sparsity. This is called an elastic net problem. And the constraints are, one, that we would like to have non-negative entries, and two, that we would like the diagonal to be 0, which means we're learning a hollow matrix, and the reason we do this is to avoid trivial solutions. So now let's start talking about our method. So now, in our model, if user U belongs to user subset P sub U, then the predicted rating for user U and target item I, it is, if you see our U transpose SI, it was what was before in SLIM. Now we have two parts. We have the global part with RU transpose SI, and also we have the local part, which is RU transpose, and now we're taking the ith column of the item-item model, which corresponds to the subset P sub U. So this means we do not take all of the local models. For the user U, we use the local model which corresponds to the subset this user belongs to. So you can see here the global and the local part, and there's also a variable called GU, which stands for the personalized weight that for this user, the global and the local parts will have an impact on. GU is a variable that varies between 0 and 1. We can see that when GU is 0, this means that only the local part plays a role. When GU is 1, only the global part plays a role. And now the overall model. Here we have minimization of the error. We also have L2 and L1 regularization for both the global and the local part. They are actually independent, these regularizations, again, to prevent overfitting and enforce sparsity. And we have, this is subject to the following constraints. As we said, GU to be between 0 and 1. P sub U is the variable that shows the user assignment, and this can be one integer in the set 1, 2, 3 towards K. K is the number of user subsets. And then S is the global item-item matrix. S1, S2, S3, etc., Sk are the multiple local item-item matrices. Again, K is the number of user subsets. And the constraints are the same that were in SLIM. We would like these item-item matrices to have non-negative entries and also to have the diagonal to be 0 to avoid trivial solutions. So you can see that we learn all of the variables, the global matrix, all of the local matrices, the vector P and the vector G. Vector P is a vector which is of size as the number of users, and vector G the same thing. It is as long as the number of users. And for every element of P, this corresponds to user U, and it has the assignment of this user, and every element of G corresponds again to user U, and it has the personalized weight of that user. So now how the variables are estimated. So in our model, we're using alternating least squares. Here in this simple a little graph, we can see that we estimate the models. This means estimating the global and all of the local models. And then when we fix them, we go to update the user subsets. The way we update the user subsets is in a k-means type of approach, where we try for every user, every possible cluster, and we compute the value of the objective function for that cluster. So for every user, we go, OK, this is the value of the objective function for the first cluster, the second cluster. We assign him, after all, to the cluster, which gives the smallest value of the objective function. And when we do this, we also update the personalized weight GU. The way we update the personalized weight GU, it is very simple. We just take the derivative of the first equation there, and we set it to 0 for all of the items, rated and unrated. And this is an iterative algorithm, so we continue this until convergence. And when does convergence occur? When no users switch subsets, or a very small percentage of the users switch subsets. This is normally in our method we have said to be around 1%. And the initialization of the different subsets is done by doing a general clustering on the training matrix by just a k-means approach. So now we describe the model. We are ready to talk about experimental evaluation. So we have tried our method on different data sets. Actually, beyond these 4 data sets, we also have a 5th one, Jester. We do not show results here on this presentation, but the trends are exactly the same as the ones you'll see here. The groceries data set is a transaction from a grocery store transactions data set. The rest, Movie Lens, Flix, or Netflix are movie data sets, and the Jester is a small joke data set. And also, I would like to point out that the matrices in all of these are binary. So we just have 1 and 0. We have implicit feedback. So either how someone has purchased or rated something or not. We do not have explicit data. So the evaluation methodology is we employ a leave one out cross-validation approach, where for every user, we take one item, we hide it, this is in the test set, and now we are trying to recommend to this user this test item. So in his top N list, we would like to have this test item. And the way we measure the quality is with 2 ways, with hit rate and average reciprocal hit rank. Hit rate shows the percentage of the users that actually had this test item recommended to them in the top N list, and average reciprocal hit rank also takes into account the position that this test item was recommended in the top N list. So if the item was recommended in the first position, it will have a bigger weight. The lower the test item is recommended in the top N list, the lower weight it will have. And we compare our method against 3 methods that have shown to perform very well on top N recommendation. Pure SVD, it treats the missing values as zeros, and then it computes a truncated singular value decomposition on the training matrix. BPRMF stands for Based on Personalized Ranking and Factorization. So it uses the ranking loss to compute matrix factorization, and we've talked about SLIM. And then we've done an extensive search over the parameter space. So this means that both for our approach and for competing approaches, we've tried different values of the parameters, and here we're going to present only the best results. Now, because our method is actually has a lot of components to it, we are going to show how the other things work, how the different components actually, what impact they have. So local SLIM without refinement, it means we only have local item models, no global. Also, no personalized weight, and the users cannot switch subsets. LSLIM doesn't have the global component, but the users are allowed to switch subsets. And GLS SLIM R0, it has both global and local, and personalized weight, but the users cannot switch subsets. In experimental results, we can see here that GLSLIM outperforms the rest of the proposed methods as expected for all of the data sets. And actually, if we compare like LSLIM R0 with GLSLIM R0 and then LSLIM with GLSLIM, we will see the impact of having the global component. If we compare LSLIM R0 with LSLIM and then GLSLIM R0 with GLSLIM, we will see the impact of allowing the users to switch subsets. And while in the majority of the cases, allowing the users to switch subsets has a less impact than adding a global component, if we add all of them together, we have the best possible performance. And here we saw the best results over all possible different for just the best number of clusters. Here we want to see what happens for all of the different kinds of user subsets. So we can see that GLSLIM outperforms the other proposed methods for all different kinds of user subsets. It is not just that for one, it does better. And also, I would like to note that when the user subsets is 10, we get 95% of the best performance of GLSLIM overall, which means that we do not have to have very many user subsets. Even for 10, for our data sets, it showed to perform very well. And now, up until now, we saw the performance by starting the users, as we said, by clustering the training matrix. However, we want to see how tied is the good performance of our approach to this specific initialization. And in order to check that, we started by using random user subsets. So now we can see that with the blue line that shows with random initialization, that in the first iteration, we have a much lower hit rate than when we normally start with clustering, which makes sense because the user subsets now are random. And then it also takes many more iterations until convergence. However, when it reaches convergence, we can see that the hit rate achieved is actually very similar to the hit rate achieved with starting with like a k-means initialization. And from that, we can conclude that our approach is not tied to only a very specific initialization, but it can handle different. And here are the last experimental result slides, the performance against competing methods. We can see that it outperforms the rest. I would also like to note, although it's not here as shown in this example, that our simplest method, which is local SLIM without refinement, which just uses the multiple item local models, still outperforms the best competing approach for our data sets, which shows the value of using multiple item local models. So conclusion. So GLSlim is an item-based method which improves upon item-based schemes by capturing the differences in the user preferences. And the experiments show that GLSlim outperforms competing top and recommended approaches. And if we see all the different proposed methods and we see all of the components, we can see that all of the components actually help improve the performance, both using multiple item models and having the global component with a personalized weight and allowing the users to switch subsets. Thank you. Any questions?
I know there was a lot of information packed in that presentation, so there has to be questions. One over there.
Great presentation.
Thank you.
So, but tough time following the word. I think I probably missed this part when you spoke about it. How do you go about, it's an implementation detail, but how do you go about like initializing? How do you determine number of cluster, the K value to start with in terms of like determining the user clusters? And then you spoke about how you build item to item for each one of these clusters, right? So can you talk a little bit more about those details?
Yeah, of course. So the initialization was done by using just the training matrix. So we take the training matrix and we cluster the users. So think of every user like an example, and the different items are the different features. So we cluster it like that. We used Pluto. This is a program that does a spherical k-means clustering. And so like that, we have the initial user assignment. Now, the K, like how many is the user subsets, it is a user-defined parameter. So you decide if you would like to try this with 5 or 50. And now after that, for every single different user subset we have, we go ahead and we compute a separate item model. So think for every user subset, you will have your own item model, and then you will also have a global item model for all of the users.
Okay, there's another question over here. Can you stand up, please?
Thank you. It's very interesting work. I'm very curious about like scalability of the model you proposed. So does it can handle like a real large number the scale of data set? Thank you.
Thank you. That's a great question, actually, because I also forgot to mention it in the presentation. I'm not sure if I can go back. But anyway, if you remember the overall model, I showed it in matrix notation, where we minimize for all of the different matrices. However, we can learn every item, so every column independently. So then we can, if you have like parallel resources, you can actually parallelize. The way I've run these things is by parallelizing over all of the different items. And the idea is that if you see completely algorithmically complexity-wise, the complexity of learning all of the multiple item models is 2 times the complexity, actually is exactly the complexity of SLIM, because we're talking about the same training matrix. So we'll have once the complexity of SLIM for the global model, and then one additional the complexity of SLIM for all of the multiple item models. And then we also have the complexity of changing the users to the different subsets.
Question over there?
Yeah, I got a question here. Very interesting talk. I'm just wondering, so there are a lot of effort in RecSys trying to cluster users, right? So you propose a method that you eventually got clusters of users. Have you compared this with the initial Pluto user clusters? And is this clustering better suited for, say, co-star scenario? Have you looked into that?
Thank you. So we actually initialize with Pluto, like with the user subsets. That's how, I'm not sure if I exactly understood. So I do not really check the quality of the clusters, if this is the question at the end of the day, to see if the clusters that we have in the end of the convergence, if they're like better clusters than the Pluto, I guess, clusters. We start with them, and as you saw, we also start randomly. And for us, the main motivation is to have the best possible performing method in terms of model learning, not the quality of the cluster, if that answers. Okay.
So following on that question, have you tried, or did you try within Pluto trying to use different clustering algorithms, or you just went with k-means?
I just started with this initialization. And I didn't try any other kind of clustering initialization. The equivalent was that we did the random to show, oh, okay, even with another kind of initialization, the method still works.
The other question I have is, you have this 2-step approach. The first one is you do the clustering. The second one, you apply the local models and the global one. How much can you generalize that approach? I mean, you could think about doing that with not only SLIM, with any other approach, right? Have you thought about that?
Actually, we have. We might have like a follow-up work in this, to see how other algorithms, not SLIM, and maybe not even item-based, would work with a problem like that, but I haven't done it yet.
Great. So let's thank the author again. Thank you.
Thank you.